Electrode potential. When passing an electric current in the electrolytic cell, redox reactions happen where the flow of electrons between metal and the metal ions in the solution occurs until equilibrium is established. We mean by the equilibrium the rate of gaining electrons equals the rate of losing electrons. The redox reactions are driven by the difference in the number of electrons between the metal and the metal ions. We call this difference the potential difference or the electrode potential. In non-reactive metals, the equilibrium lies further over to the right. For example, copper ions gain electrons easily and readily reduce to copper metal. On the other hand, for reactive metals, the equilibrium lies to the left. For example, zinc metal loses 2 electrons easily and oxidizes to zinc ions. When metal is dipped in the solution of its ions, the difference in the electrons causes the electric current to flow. But how can we measure the electric difference or the electric potential voltage that is established between the metal and its metal ions? We can't measure the electric potential directly. That is why we measure it in relation to another system. This system we usually use for comparison is the standard hydrogen electrode. What is the standard hydrogen electrode? The standard hydrogen electrode is a half cell that can be used as a reference electrode. It consists of hydrogen gas at 101 kilopascal pressure in equilibrium with hydrogen ions of concentration 1 mole per cubic decimeter. A platinum electrode covered with platinum black in contact with hydrogen gas and the hydrogen ions. The platinum electrode is covered with a glass bell that contains a hole for hydrogen to bubble out. When connecting the hydrogen electrode with another cell, we assume the reading of the hydrogen electrode is equal to 0, because platinum electrode is inert and doesn't take part in the reaction, and the value read on the voltmeter belongs to the other half cell. We can see from the equations that the hydrogen half cell is balanced and doesn't make difference to the value of the standard electrode potential of the other connected cell. To measure the standard electrode potential for non-reactive metals such as copper, we can combine the copper half cell with the hydrogen standard cell. We place a pure copper rod in solution of copper ions, for example, copper sulfate solution, and we connect the copper cell with the hydrogen cell by connecting wires between the platinum rod and the copper rod, salt bridge that connects the two solutions to complete the electric circuit. By connecting the two solutions containing ions, we connect them without allowing electrons moving through the bridge. The salt bridge can be made from a strip of filter paper or other inert porous material soaked in a standard solution of potassium nitrate or potassium chloride. The copper is considered to be the positive pole and the hydrogen is the negative pole. Once the circuit is completed, the voltmeter gives the reading 0.34 volts. If we looked at the reaction at the positive terminal, we can see that copper ions takes 2 electrons to form the copper metal. And at the negative terminal, we have hydrogen molecule in equilibrium with 2 hydrogen ions and 2 electrons. The standard electrode potential values show us that copper ions are easier to be reduced than hydrogen ions. Copper ions gain electrons from hydrogen half cell, where hydrogen ions lose electrons to the other half copper cell. Same reaction happens for all metals below hydrogen in electrochemical series. For elements above the hydrogen in electrochemical series, the opposite happens. For example, zinc is above hydrogen in electrochemical series. When zinc half cell is connected to standard hydrogen electrode, hydrogen is considered to be the positive pole and zinc is the negative pole. The hydrogen is reduced and gain electrons at the positive terminal. Zinc is oxidized on the other hand and loses electrons at the negative terminal. So how can we measure the electrode potential of non-metal ions? When the two half cells are hydrogen and non-metal, such as chlorine, platinum foil is used as electrode in both cells, and the measured volt is the volt of the cell connected to the hydrogen cell. For example, when a standard hydrogen electrode is connected to chlorine half cell, we can see that chlorine molecules are easier to be reduced than hydrogen ions, and that chlorine molecules gain electrons from hydrogen half cell. We can use the standard electrode potential values to predict the cell voltage. This happens when the two connected cells, both of them are not a standard hydrogen electrode. The difference between the two half cells voltage is called the standard cell potential. We can predict the standard cell potential from knowing the voltage of each standard half cell. For example, we know that the standard silver cell potential is equal to 0.8 volts, and the standard zinc cell potential is equal to negative 0.76 volts. We can predict the voltage of this cell by subtracting the standard electrode potential of zinc at the negative pole, 0.76 volts, from the standard electrode potential of silver at the positive pole, 0.8 volts. This will give us that the cell potential is equal to 1.56 volts. The silver is blue zinc in electrochemical series. That is why silver is considered to be the positive pole and zinc is considered to be the negative pole.